Welcome to another fabulous day in Calculus 3, where we're going to do Green's theorem. Very powerful theorem. Yeah, it lets you do line integrals without doing a line integral, but a lot of conditions have to be in place first before you can even apply Green's. So let's go look at some of the preparatory work and some definitions, and then we'll look at what Green says. Yay. So we're going to define a simply connected region before we can state Green. So recall, you guys already know what a connected region is. It's basically not Hawaii. It means any 2 points in the region can be connected by a piecewise smooth curve lying entirely within a region. Well, okay. Then what is a simply connected region? It's a region that looks like this. This is simply connected, and these two regions are not. Well, how come? You're not ready yet. We need a definition, and then we'll define exactly what it means to be simply connected. First, let's define a simple curve. A curve C given by some parameterization there, R of t is equal to x of t, y of t, where time goes from a to b seconds, is simple if blank. It does not cross itself. Fill in the blank. It does not cross itself. Ooh. So what does that mean? It means that R of C is never equal to R of D for any C and D in the open interval, A to B. Okay, fine. Now let's define a simply connected region. A plane region R is simply connected if its boundary consists of one simple closed curve. And so that's why we needed the simple here. It's a closed curve. We already just learned what a closed curve is in the last section. The starting and stopping points are the same, but it's a simple closed curve. If not only is it closed, it doesn't cross itself. So I hope you can see that in this diagram here, the boundary of this simply connected region is a nice curve. It never crosses itself. It is closed. Now, these guys over here, like this guy is violating the simply connected definition because it's got more than one border. It's got three borders because it's got a couple of holes in it. It's like Swiss cheese. And then, of course, this is definitely not good because you've got it crossing itself there. So this first is not simply connected because it has more than one closed curve to capture the entire boundary of the region. And then this here crosses itself. So both of those yellow ones are not simply connected. Well, what the heck? Why do we need the simply connected? Because we need it for Greens. So now you're ready for Greens. Oh, hang on. Okay, now today's your big day. Yeah, it's a big day for you. I'm excited. Green's theorem. Big theorem. Very powerful. You can brag about this one after you actually learn it, okay? Yeah, it's your next cocktail party. Congratulations, you have bragging rights because you now are going to learn Green's theorem. Here we go. Okay, you need a region R, and it has to be simply connected. You got to have a smooth boundary. Okay, and here's the weird part. Yeah. Oh, piecewise smooth. Okay, also. It has to be oriented counterclockwise. What if it's oriented the other way? We'll talk about that later. You want the curve to be traversed once so that when you move around the boundary, let's say here, that if you were driving around this island, you could look over your left shoulder as you were driving counterclockwise and see the land over your left shoulder. That's the important part. Okay. And then, of course, if your M and N from your vector field have continuous first partials in your open region containing R, then if you're doing this line integral, and I'll put a little closed here because it does have to be a closed curve. And this could be differential form, or it could be an FDR, either one, because they're essentially the same. Then it's going to be equivalent to this double integral. Yeah, you didn't think double integrals were coming back, did you? Ah, here they are. The double integral of dn dx minus dm dy dA. That's your area element. There is greens. Yeah. Now, some vocabulary, just throw this in there for now, and then it'll make more sense as we go the rest of the week. These line integrals here are known as circulation line integrals. And then this right here is a curl. Just write this down for now, and then later on when you read your lecture notes, it will make sense. I'm going to do a partial proof, and then we'll do some examples. Okay? Partial proof, and then some examples. Okay, so in plain English, what does Green say? It says that, let's say you're trying to do a line integral, and if all the conditions are met, you got a closed curve, and it's over a simply connected region, then go ahead and don't evaluate the line integral. Instead, do a double integral over the simply connected plane region, because that's determined by the value of the line integral over the closed boundary. Yeah. So the partial proof is going to look like this. I got to draw a diagram. So let's say you had some really weird region here. We'll call this curve C1, and it's given by, say, y equals f1 of x. And then this will be A, this will be B, and then it has to be closed. We got to end up ending this curve where we started. So let's just say it goes and ends up where we started. So there's C2, and let's say C2 is given by y equals f2 of x. Okay, this is the region here. Okay, so the partial proof is going to look like this. We're just going to look at not mdx plus ndy. Let's look at half of it. Let's look at just the mdx over the closed curve. So since this boundary has two piecewise smooth parts to it, we're going to actually have to do two line integrals, one for the C1 and one for the C2. Ooh, that's weird. Okay. Now the C1 is starting here at x equals A and ending at x equals B, and the M, which is a function of x and y, but instead of putting x and y here, because we're on this curve where y is equal to f1 of x, I'm going to replace the y with f1 of x, and then we'll do that. Plus, and then the second line integral, you're starting at x equals b, and you're going back to x equals a. You're basically going backwards. So our lower limit is b, and our upper limit is a. And this m is evaluated at xy, but the y here is f2 of x. Now, something that you learned back in Calculus 1, we're going to use a Calculus 1 property here of integrals, and that is if you flip the limits, so if you flip these to a to b, then it'll change the sign of the integral. So we'll just change that plus to a minus, and then we still have mx f2 of x dx. Okay, fine. But now these two integrals have the same limits, and they're both with respect to x. So we're just going to put all of it into one big integral, because we can do that. Okay. Yeah, so what? So I'm going to save that for later. Let's stop there. And then on the other hand, OTH stands for on the other hand. On the other hand, let's look at, so when I'm doing greens here, I want to look at the right-hand side of greens, which involves a double integral. And since we're only looking at half of the line integral, the part that involves the m, let's just look at the m part of the double integral. So you got this double integral r, and let's just look at the dm dy portion only. Okay. If you were trying to iterate this integral, the region tells us that x is going to go from a to b, y is going from a lower limit of f1 of x to an upper limit of f2 of x, and then dm dy stays the same, and then we have dy dx. Okay, fine. Well, what the heck? Well, we're going to integrate. Well, can we do that? Sure. So we're going to do the innermost integral first. So I want you to notice here that we're integrating a derivative. What do you know from the fundamental theorem of integrals, or yeah, from Calc 1, when you integrate a derivative?
They cancel out each other.
Yeah, they cancel each other, and so you're just going to get m. Well, what do you mean? So we still have the outermost integral a to b, dx. But what we have there is in that innermost integral is we've got m, x, y, and we're going to evaluate it going from a lower limit of f1 of x to an upper limit of f2 of x, like that. And then we substitute these into the y, since we just integrated with respect to y. Okay. So I'm going to keep going here. So I'm going to still have the outermost, and then what do I have here? I'm going to go m x comma something minus m x comma something, and then I'll have dx. So I'm going to substitute those limits. I've got f2 of x, and then I've got f1 of x. Okay, stop. Now I want you to compare these two things. There's some similarities and there's also some differences. So what do you see are similar and what do you see are different? You notice they're both with respect to x, right? And they both have the same limits, a to b. But this one here is mx f1 of x minus mx f2 of x. And this one has it backwards. It's got the mx f2 of x minus the mx f1 of x. So what can we say? What we can conclude is that the line integral m dx is equal to the opposite of the double integral over the region dm dy. And that takes care of the negative. What you see how you have this negative here in front of the dm dy. When you do a similar thing for the ends, the other half of the proof, you don't end up with a negative. You end up with it equal to the positive dn dx. So I'm going to stop there, and that's a partial proof of Green's. Yay! And now I'm going to do one problem with Green's, and then we'll call it. Okay, that'll be enough for the day because it's going to take me a while. That's not a quick problem. No, sorry. So we're going to do what's called a verify. When you do a verify, that is telling you it's going to be a hard problem because that means you have to do one side of the problem and then the other side. So what they're asking us to verify here is they want us to look at this line integral and verify that Green's really does work. So they're giving us a curve that is actually the union of two separate curves. Uh-oh. So the first part of the curve starts here at 0, 0 and goes to the point 1, 1 along the graph of a cubic. Now, a cubic is kind of curvy like that. So that's the y equals x cubed. We'll call that C1. And then it's got to be a closed curve, so you got to end up right back where we started. We're going to start from the point 1, 1 and go back to 0, 0 along y equals x. That's a straight line. Okay, we'll call that C2, and that's going along y equals x. And then here's our region here, and it does look like it's simply connected. Yeah, okay, fine. So when we do the verify, that means we have to do the left-hand side of Green's and the right-hand side. And so this is really a two-part problem. That's why it's going to take me some time. So what do I mean, the left-hand side of Green's? Look at Green's here. The left-hand side is a line integral. So we're going to use all of our knowledge of line integrals, all of it. Like, I mean, brute force everything right now. It's good review. Good review. And then we're going to get an answer. Okay, and then we'll go, okay, great. Then we're going to do the right-hand side. of greens, which basically is greens. We're going to do the corresponding double integral, and we're going to evaluate that, and we better get the same answer as the left-hand side. And that's what a verify does. So let's start. It's going to take some time. You got to do a verify. So left-hand side, LHS stands for left-hand side. So what does that mean? I got to do the left-hand side. Oh man, I got to do the line integral FDR for the whole entire curve, but the curve is piecewise. So I'm going to actually have to do two separate FDR line integrals, one for the first curve, the cubic, and then whatever answer I get for that, I'm going to have to save it for later and then add it to the result for the line integral when I go along the second curve. Okay, so this left-hand side, that's our strategy, but it's going to take some time because we're going to have to parameterize twice. Oh yeah. Yeah. Okay. So I need some more paper because it's going to be a while. Okay. I like to put verify type problems on quizzes and exams, just so you know. For those of you who are like, well, I'm going to go to sleep right now. No, don't do that. Okay, so if we're going to do this C1 line integral first, we got to parameterize the C1. I'll call it R1. And it is a function of x because y equals x cubed. And it's starting here at 0, 0 and stopping at 1, 1. Fine. Then we'll do our usual trick. Let x be t and y equals x cubed. So y will be t cubed. And then the time range that works perfectly for this problem will be time going from 0 to 1 seconds. And that matches the curve perfectly. You could even plug those endpoints into our vector valued function, and it'll make our function start at 0, 0 and end at 1, 1. Fantastic. We're going to have to go get the velocity vector R1 prime because, you know, when you do one of these line integrals brute force, you got to go get the dr, the r prime. That's easy. So we got 1, 3t squared. Fine. So now the C1 f dot dr becomes a regular integral, time going from 0 to 1 second. We're going to have to take a dot product here. You know. Now our vector field, they gave it to us disguised, and so I'm not really doing an FDR vector field. I should probably follow the differential form since that's how we're given it. This is the y cubed dx plus x cubed plus 3xy squared dy. So now what? So they did the dot product for us. You're going to do y cubed. Ooh. But y is equal to t cubed. Ooh, I know. So you're going to have to go t cubed cubed. And then your dx is the first component of your velocity vector. So that's going to be 1 dt. And I'll put the dt way out here. Factored out. Plus, now you're going to go, uh-oh, what is x cubed plus 3xy squared? Well, x is t, so you're going to go t cubed plus 3xy squared is 3 times t, and then y is t cubed, but you're going to square it. And then the dy is the 3t squared. Okay. So be careful here because we got a lot of exponents, and a common student silly mistake is to mess up the exponents, okay? You don't want to make that your silly mistake. So t cubed cubed is t to the 9th plus, I'm going to distribute this 3t squared over parentheses. So 3t squared multiplied with t cubed is 3t to the 5th. This here is 3 times t to the 6th, which is really 3t to the 7th. So when I multiply 3t squared times 3t to the 7th, I'm going to get 9t to the 9th. Okay. I'm still going from 0 to 1. I have 2t to the 9th terms. If you don't mind, I'm going to combine those because, you know, I can. And then I only have to integrate this easy peasy problem, 10t to the 9th plus 3t to the 5th. And that antiderivative is going to be what? T to the 10th plus 3/6, but that's a half. T to the 6th, going from 0 to 1. That's going to be 1 plus a half, which is 3/2. Okay, save that for later. How come I'm saving it? Because look, I'm only done doing the C1 portion. of this brute force line integral. I still have to do the C2 portion. Oh man, yeah. So we have to start here at 1, 1 and then end up at 0, 0 along the diagonal line y equals x. Okay. C2, I get to parameterize. We know that y is equal to x, so how about we're going to call this vector value function R2 of t. Let x be t, and then y is equal to x. Now remember I told you it's okay to have time going backwards if you're doing one of these vector field line integrals, and this is really nice because I'll let you do that right now. Okay? Otherwise, you're going to have to reparameterize this if you want to have time going forward. So I'm going to say it's okay to have time go backwards here, but show it and then stick with it. Stick with that lane. Don't all of a sudden in the middle flip it and have time going forwards, because then you're going to get the wrong answer. Okay? So now what? Go get R2 prime. And that's easy because it's just a constant vector. And so this C2 y cubed dx plus x cubed plus 3xy squared dy becomes the integral going from not 0 to 1. We're going to go backwards. Remember, 1 to 0, 1 to 0. That's right. And then you're going to go y cubed. Well, y is equal to t, so I'll go t cubed, and then the 1 is dx plus, and now I've got x cubed, that's t cubed plus 3x y squared, and then the dy is just a 1 also, and then this is going to be integrated with respect to time. I'm going to clean this up a little bit because I want to add like terms. It turns out that all 3 of these terms are t cubed terms. So how about if we add them all together, and then we only have to worry about 1 term to integrate. Oh, nice. 5t cubed. And then that integral is 5/4 t to the 4th, where we're going from 1 to 0. Careful here. So you're going to get 0 minus 5/4. So negative 5/4 is the answer. You can get a negative answer for line integral. We talked about that, right? So the final answer is the first integral result I had, which was 3/2, plus the second value, which was negative 5/4. And so my final answer here is 1/4. Now, are we done with this problem? No. Why not? Well, because we were in the middle of a verify problem. Oh man, you're kidding me. No. All we did is we did the left-hand side for greens. Now, folks, I rarely give a verify problem. Usually I just say go use greens, okay? And you don't do the left-hand side. But I'm trying to make a point here. You're going to see what the moral of the story is very soon, just in a few moments. You're going to go, oh my God, are you kidding me? Yeah, it's exactly your response. And I want it to be. That's exactly what I want you to say, okay? Because you'll see. All right, so now it's time for the right-hand side of greens, which says, hey, that line integral gives the same answer as the double integral over the region, as long as you have a closed curve and it's a simply connected region and all that's true, which we do for this problem. And then the integrand is going to be dn dx minus dm dy. And it'll all be the same answer. You mean we'll still get 1/4? Yes. So here we go. We're going to do the right-hand side of greens, basically applying greens. So I need more paper. Oh, yeah. So the RHS, right-hand side of greens, it says that dn dx minus dm dy. Okay, now what was the m and what was the n? Well, if you go back to the original problem, remember the m and the n are there for you. So m is y cubed and n is this sum. So let me just write that down, otherwise I'm going to forget it. You know, we've got m is y cubed and n is x cubed plus 3xy squared. So what would dm dy equal? Well, it would be 3y squared, and dn dx would be 3x squared plus 3y squared. Okay, fine. So then this integrand, which is dn dx minus dm dy. And yes, it's okay to, simplify by adding like terms. It looks like the 3y squared terms go away because the 3y squared minus 3y squared is 0. So the only thing we're going to have to integrate is 3x squared. Well, then how are we going to do that? Well, you guys know double integrals. You're experts. Yeah. So my personal favorite order of integration is dy dx. If you like dx dy, that would be okay also, because this region that we're integrating on, I have shaded in here, is both vertically and horizontally simple, but I like the vertically simple myself. So if you put a little man in here vertical, his head is on the upper limit, y equals x, and his feet are on the lower limit for y, x cubed, and x is going from 0 to 1. So it's easy to iterate this double integral. We're going to do that. So x is going from 0 to 1. The y limits are x cubed for the lower limit and x for the upper limit. Okay, let's go ahead and do this double integral. Here we go. It's good practice. So what is the antiderivative of 3x squared with respect to y? Well, 3x squared just looks like a constant. So it's just going to be y. And then you're going to evaluate y going between those limits there. So let's go ahead and do that. Don't forget to substitute your upper limit first and then your lower limit. Okay, fine. And then please distribute your 3x squared before completing this problem. We're getting close to being done. Easy peasy. This is like a calculus 1 integral now, right? And the antiderivative of this looks like it's going to be what? 3/4 x to the 4th minus 3/6. 3/6 reduces to a half. X to the 6th going between 0 and 1. And so you'll end up with 3/4 minus a half. But that's, hey, that's 1/4. And that's the final answer. Now, so my final thing on this is which do you think was easier? Was it easiest to do the line integral side, where we had to parameterize twice and add two completely separate line integral results together and do all of this work that took us like forever? Or was it much nicer and simpler to simply do an easy peasy double integral and get the same answer? What do you guys think?
Greens.
Greens is awesome. So what you should all be saying is like, wow, I love greens right now. This is what you're all saying, okay? And that concludes that example. And that concludes the lecture for today. We'll pick this up next time.